Hi everyone, this is Yuguang from E department, and I'm presenting to you my class project of this graphic model class, which is about an efficient inference algorithm in solving graphs with continuous potential. So specifically, I'm going to work on non-parametric belief propagation. So belief propagation is actually used to calculate the marginal probability of nodes and a set of nodes, the joint probability of sets of nodes. So it is composed of two steps: collect evidence and distribute evidence. So basically, we randomly select a node in the graph, and we collect all the messages from all the nodes for only once. And once all the messages reach this x1, it will distribute evidence back to their children until all the messages reach all these nodes. Let's take a close at this local message passing process. So let's say I want to pass a message from x3 to x1. So x3 needs to receive all the messages from its neighbors except for x1. So all the messages are denoted by here, the new here, and we calculate the product of these messages, and we multiply it by the potential of the edge. So then I use the equation to calculate the updated message from x3 to x1. So if all the variables, the potentials and messages, they are a discrete random variable, then it's like this edge potential would be like a table, which is a variable, which is matrix, and this messages are vectors. So it won't cost too much calculation. However, if in a lot of application we have to use continuous function to model the potentials of nodes and edges, in this case, the potentials are modeled by the mixture of Gaussians, which is the summation of weighted Gaussian function. Good news is Gaussian mixture is still the mixture of Gaussians because the product of Gaussian function is still Gaussian, and the mean and covariance and weights, they could be calculated by using equations right here. But the problem is if we have D input mixture and each mixture is composed of m Gaussian components, then we might end up with m power d Gaussian components in the final mixture, which will take a lot of computer memory and take a lot of time for this calculation. But what if we don't use Gaussian mixture? We use the discretization of this continuous function. Then it's actually durable if the potential of the node is one-dimensional. Then we don't need too many samples from here, and we could do it in a discrete way. But if the variable is high dimensional, let's say 2 dimensionals or 3 dimensionals, then it's become harder and harder to finish this discretization process and get too many states. When you do the multiplication, it takes too much time. So in this class project, I'm still stick to this previous method using this Gaussian mixture to denote to describe the random variable. The problem is how to efficiently compute message with this assumption while maintaining the accuracy. So specifically, I'm going to apply a method which will handle the calculation of taking the product of the Gaussian mixture and calculate it efficiently. Here comes the method, non-parametric belief propagation. So in this method, it still assumes the potential function are weighted Gaussian mixture. Instead, the MVP didn't use analytical method to calculate the product of Gaussian mixture. is actually use Jeep sampler to first take sample from the product density. And we use the kernel density estimation to create a new description of the product density, and use this to proceed in this process. So here's some example of Jeep sampling. Let's say this discrete random variable, in this case here. So we have the distribution of A, so then I randomly take a sample of A, and based on the states of A, I'm going to use the conditional probability here, and find out that find out the sample of B and find out the sample of C, and now I get the states of B and C. I could build a new conditional probability based on this B and C, and we find another sample like D. So then I take a set of sample A, B, C, and D, and repeat this process again. Finally, this distribution, the samples, they have the distribution like this joint distribution here. So when we use the Jeep sampling in continuous random variable, it's actually follow the same rule and the same idea. However, it's the method to take the samples according to a continuous distribution is a little bit different. We first select this omega here, and then we create a random variable, a sample, which is something which is in accord to the normal distribution. So after we have a set of samples which have the distribution according to the product of Gaussian mixtures, which might have a histogram looks like this, we will use kernel density estimation to describe the new distribution. So kernel density estimation assumes that this distribution is the summation of different kernel functions, and this kernel function is actually, in our case, described by Gaussian functions. It have its center, like I show in this case, it have the center, it have its bandwidth, but its bandwidths are all the same, and they have this weight. So what I will do is to use the rule of thumb heuristic to predict the bandwidth, and I figure out the center of it, so that given a distribution, I may use Gaussian function to describe this distribution again. Because MDP is able to handle the graph with continuous random variables, so it has been used in a lot of field of computer vision. Specifically, this author, he used MDP in articulated body tracking. Actually in this paper, he developed some new method to substitute the Jeep sampler, which is the mod propagation and kernel feeding. The key idea here is to merge indistinguishable component by mod detection. Well, this method accelerates the classic MBP for quite a lot by using non-parametric belief propagation. Even though with few nodes, like 5 nodes, it takes way longer time than the Gaussian belief propagation. But if we have a decent amount of nodes and decent amount of edges, the calculation time, the execution time of the MBP code won't increase too much. So it's in terms of the computation efficiency, it could handle more complex graph than the classic method. Then I evaluate the calculation accuracy of my MBP code with the analytical calculation result, which is calculated by the Gaussian belief propagation. And I use this parameter to evaluate the error. You can see that this 5-node case, it have an error of 6.7%. However, when I applied my MBB code on more complex graph, which composed of these 10 nodes, the result looks very weird because the kernel density estimation function is not stable. I figure that it's because there are some parameters I still didn't get how to set the optimal value for it. So probably in the future, I will fix this problem by fix the kernel density estimation function. So that's about my project, the non-parametric belief propagation. Thank you.